Hello, and welcome to this group's presentation on circular patch microstrip antennas. This is group B23. Our members are Ismail, Nick, Brandon, Susie, Ahmed, and David. I'm going to start by giving a quick overview of our presentation. First, Nick is going to speak to our design and simulation of our antenna itself, followed by Ishmael talking about our OpenEMS code, and then Susie's going to talk about some of the advantages and disadvantages of our type of antenna we decided, as well as the dimensions and methods of feeding the device itself.
I will be discussing the design and simulation of our project. So first we have a rough design of our circular patch antenna. And so on the outside you'll see the substrate, and on the inside the yellow, the gold component of the project, that would be our circular patch. Also we represented the coaxial cable with the copper and blue images. And so I wanted to go over dimensions as well. So this was a little tricky and we needed some equations to really figure it out. But first, our substrate thickness. I read in one paper that it had to be smaller than 1.96 millimeters because we use the frequency of 2.1 gigahertz. So we decided to just stick with 1 millimeter as our substrate thickness. Our substrate radius, we chose 45 millimeters. It was really arbitrary. It didn't really do anything in our we didn't really find use for it in any calculations. And in OpenEMS, it didn't really matter what it was, but we thought we'd do it to scale compared to all of the other dimensions. So the circular patch antenna radius, we calculated A was 24.997 millimeters, but we decided to use the effective circular patch antenna radius calculation, which equaled exactly 25 millimeters. And so our resonant frequency, earlier I said it was 2, but we actually used 2.12 gigahertz. And so finally our dielectric constant we used as 13.65, and that really allowed our graph to have no overshoot and to be an ideal antenna signal jammer. So here's the page with all of our dimensions and equations. So right here is an isometric view of our circular patch antenna. Right here is just really showing the thickness, the 1 millimeter thickness which we chose of the substrate, and also in turn our patch. Then here we just wanted to give a nice detailed view of all the radii of our circular patch and signal jammer. So on the outside you have 45 millimeter substrate radius, which is this outside right here. Then this inside radius represents our circular patch antenna radius, which we chose effectively to be 25 millimeters. And in the middle here we did some research on some coaxial cable dimensions, and we found that most radii are about 13.43 millimeters, and we decided that it will be directly in the center of our circular patch. And just to complete the drawing, we had professional, drawn by us. Our project name also is PB and Jammers, and our circular patch microstrip antenna drawing. Here is the page of equations that we used. So the first one here, the F, was just a constant that you need to calculate A, the radius of the patch. And so once we calculated F, we're using a frequency of 2.12 gigahertz, and our dielectric constant was 13.65. We found A using this whole equation we found in multiple papers proving that these are the dimensions you need for a functioning circular patch antenna. And then we use A to calculate the effective patch radius. And here are two other equations just to reassure our calculations. So H, you also needed the constant of the speed of light, which is around 3 times 10 to the 8. And so the thickness of the substrate has to be smaller than we calculated 1.96 with our dimensions. And also the frequency component has to satisfy this huge equation, and so we did that just to solidify our calculations, and so it came out to 2.12 gigahertz precisely.
Okay, I'll be talking about implementing our design into MATLAB or OpenEMS. So first off, after Nick completed his calculations, we defined them in OpenEMS. That's the first part of the code. One thing I want to draw your attention to is epsilon r, substrate.epsilon r, and all that is the electric permittivity. Next, we talked about feeding. We chose a coaxial cable coming from below into the center of the antenna. We'll talk more about that later on. So next part was the FDTD excitation and the CSX CAD or CSX CAD. We initialized our FDTD with 5 times 10 to the 4th time steps and an end criteria of 1 times 10 to the minus 5. Also note that we defined it in cylindrical coordinates. We gave it a sinusoidal excitation of 100 megahertz. The frequency is 100 megahertz. And we set our boundary conditions to PEC, which stands for perfect electric conductor. Next is the CSX CAD, which we also define in cylindrical coordinates between 0 and 2.4 for the radius, phi was between 0 and 2 pi, and z was between negative 1.2 times the substrate thickness to positive 1.2 times the substrate thickness. And we use 25 time steps for all of them. Next, we set up, in this part of the code, we set up the geometry onto the CSX CAD and we excited it. So we added the circular patch and the ground plane using the add box function. We only did a slight modification by adding the coord system 1, which tells the function to define everything in cylindrical coordinates. We then added a new material for the substrate by using the add material and then giving it all the proper parameters. We used the lump port to collect the voltages and currents, which we'll be using later on for our calculations. The next part of the code is where we ran our simulation. One thing to notice is where we defined our U. So U is our voltage and I is our currents, which obviously we'll be using those for our calculations later on. The next part is where our results were processed. We calculated our reflection coefficient and impedance. I'll be talking about the results later, but one thing I want to show you guys is the output of the CSX CAD. So as you can see here in the top view, we have our coaxial cable in the middle, our circular patch that just surrounds that, and on the outside the circular substrate. From the bottom view you can see the ground plane. And now back onto the results. So the first graph is the impedance graph. This graph shows the imaginary part of the impedance of the antenna being dominated by the real part at the resonant frequency. So it shows that the antenna is operating at around 2.1 gigahertz. The next graph is the reflection coefficient, also known as the S11 parameter graph. This antenna it calculates the frequency at which the antenna is operating, and as you can see here it dips down, which means at 2.12 gigahertz all the power is reflected from the antenna, or reflected means transmitted, and that's the frequency of operation of our antenna.
So I'm going to be talking about the advantages and disadvantages of the circular patch microstrip antennas, and I'll start off with the advantages. So first of all, they're inexpensive because of their simple structure, and they provide higher gains than a single patch. An advantage that these kinds of antennas have is their ability to have polarization diversity. So they can be designed to have vertical, horizontal, right-hand circular, and left-hand circular polarization. And this is done using multiple feed points or a single feed point, and that makes them really useful and able to be used for a lot of different purposes. and they're compatible with planar, microwave, millimeter integrated circuits, and monolithic microwave integrated circuits. As well, they're low in weight, and they are capable of dual and triple frequency operation. And finally, feed lines and matching networks can be fabricated easily because they are simple structures as well. Now for disadvantages. So the circular patch microstrip antennas are low in efficiency, and they have lower gain than conventional microwave antennas. They have a large ohmic loss in feed structure, low power handling capacity, excitation of surface waves, polarization purity is difficult to achieve, and complex feed structures require high performance arrays. But some of these effects of disadvantages can be minimized. So I'm going to be comparing the circular patch microstrip antenna with a few other antennas. So I'll be comparing it to the microstrip slot antenna and the printed dipole antenna. So all three of these antennas have a thin profile. Their fabrication is easy, although the microstrip circular patch antenna is much easier. And in polarization, the microstrip patch antenna and the microstrip slot antenna have both linear and circular polarization, whereas the printed dipole antenna only has linear. So that makes the microstrip circular patch antenna more flexible. And dual frequency operation, it's possible in all three. For shape flexibility, the microstrip patch antenna can be made in any shape. That's why we have the circular microstrip patch antenna. And whereas the slot antennas are mostly rectangular and circular, and the printed dipole antennas are rectangular and triangular. Now, the spurious radiation exists in all three, and the bandwidth for the microstrip patch antenna has a greater bandwidth, so it's 2 to 50%, whereas the microstrip slot antenna is 5 to 30%, and the printed dipole antenna is around 30%. There are different kinds of feeding techniques used in the circular microstrip patch antenna. So the four main kinds of feeding that they may use are coaxial probe feed, microstrip line, aperture coupling, or proximity coupling. So for the coaxial probe feeding method, in this method, the inner conductor of the coaxial is attached to the radiation patch of the antenna, and the outer conductor is connected to ground plane. And the advantages of this type of feeding is it's easy to fabricate, easy to match, and its disadvantages is it provides a narrow bandwidth, and it's difficult to model specifically for thick substrates. So for the microstrip line feeding technique, it's considered one of the easier methods to fabricate, and it can be considered an extension to the patch. What it is it's just a conducting strip connected to the patch, and it is simple and easy to match. However, it can be disadvantageous because it puts a higher limit on bandwidth and it increases the thickness. So for the aperture coupling method, now this method uses two different materials that are separated by a ground plane, and the lower material is coupled to the patch using a slot in the ground plane that separates the two materials. And then the ground plane is used in the middle, which isolates the feed from radiation element and it minimizes the interference. And then the top plane uses a low dielectric constant. And the benefits of this method is that it allows for independent optimization of feed mechanism element. However, this method can be very difficult to achieve. So the proximity coupling method, this method has the largest bandwidth range. However, it's very difficult to achieve, and that's because it can be very difficult for the two materials to be perfectly aligned. And these two materials are lined up using the feeding stub and the width to length ratio of the patch. And so because of the type of material, it can be really difficult to match them up exactly. And this method can have a disadvantage in that it makes the overall thickness of the antenna much larger.
The circular patch antenna, as you can see from this diagram, consists of a ground plane and a patch with a dielectric material between them. Generally, the radius of the patch is the determining factor in the antenna's operation. For our project, we focused on designing this antenna for the purpose of cell phone frequency jamming. As such, the bandwidth and frequency must be set within certain parameters to achieve this goal. There are three common methods for the analysis of these patch antennas. Typically, the system can be modeled through either the transmission line model, the cavity model, or the full wave model. Each of these analysis methods offers a particular benefit, whether it be simplicity or accuracy or any other benefit. The cavity model, which is one of the most popular methods used, is a highly accurate result that highly resembles radiation patterns in the physical realization of the antenna.
Okay, so just to conclude up, our microstrip patch antenna offers a very compact solution that can be used quite easily to implement our product, especially on a very short range basis. With the appropriate integrated circuit, a white noise function can be produced at a specific frequency that will jam incoming cell phone signals, or realistically any signals, Wi-Fi, Bluetooth, whatever you wanted to jam. And through our OpenEMS simulation, it can be shown that this antenna will function within the parameters of our design itself. Thank you for watching. I will just finish off by showing the references page. You can pause the video now if you do need to look at any of our references.